More today's topic, polar equations. We're checking for symmetry, then we're doing a lot of graphing. Let's jump right into the next problem. We got r squared is equal to 4 sine theta. That's another lemniscate. It's another lemniscate that we're graphing, but this time instead of working with cosine, we're working with sine. As we did in the last problem, let's check for symmetry. Let's first check for symmetry across theta is equal to pi over 2. This were rectangular coordinates, we would say the y-axis. We say the y-axis. Check to see if it's symmetric about the y-axis. But when you're working with polar equations, we call this theta is equal to pi over 2. All right, so let's substitute in this check for the polar axis first here. R negative theta. Y, well, let's check first. Let's check across the pole, negative r theta. Let's check if it's symmetric about the pole first. All right. So one of the things that I'm doing is I am aware of the identity sine negative theta is equal to negative sine theta. I am aware of that. I'm also aware that cosine negative theta is equal to the cosine of theta. So that's why I'm jumping straight to this polar coordinate that has a positive theta. Because I know if I have a positive theta, r squared is equal to 4 sine theta. If I have a positive theta, 4 sine theta will remain unchanged. And if I substitute in a negative r up here, that will, r squared will remain unchanged. So I'm sort of using my understanding of trigonometry that students who study this topic would always already have a handle on. So we have a negative r squared. I'm substituting in negative r theta is equal to 4 sine of theta, yielding r squared is equal to 4 sine theta. Notice how we end up with the same exact equation that we began with. So this is symmetric about the pole. I used negative r theta because I used identities that I'm already familiar with to substitute into r squared 4 sine theta with an understanding that I would end up with the initial equation that I'm working with. If you did that for checking across for symmetry across the polar axis, you would discover that symmetry confirmation would not be able to be determined there. Let's just show you what I mean. R squared is equal to 4 sine theta. If you substitute in r and negative theta, r squared is equal to 4 sine negative theta. You end up with r squared is equal to sine of negative theta. We've already discussed that the sine of negative theta is negative. So you end up with negative 4 sine theta. Notice how you end up with something different. However, my experience has been, if that is the case, and in the future I won't even test r negative theta, what I'll do is immediately jump to the other way of testing for symmetry across the polar axis, which is to use a more intricate, for lack of a better term, it's a more involved way of checking for symmetry. All right. If trying r negative theta won't work, I'm asking my students to also attempt to try negative r pi minus theta, that polar coordinate, even if this first approach does not work. So let's try it again. R squared is equal to 4 sine theta. All right, so now what you end up with, let's substitute in negative r squared is equal to 4 times the sine of pi minus theta. Pi minus theta. So you end up with r squared. You'd have to know the identity or the ability, you'd have to have the ability to expand the sign of pi minus theta. That's something that would need to be understood before you attempted to graph these kinds of problems. So you have the sine of pi, cosine of theta. I'm expanding sine pi minus theta right now. Minus cosine pi sine theta. All right. So now what you have is you have r squared is equal to the sine of pi. That's 0. The sine of pi is 0. So you end up with 4, and you end up with times the cosine of pi is negative 1. The cosine of pi is negative 1. So this negative 1 times that negative is positive. Bring down the sine theta. Notice how you end up with the same thing that you had before. R squared is equal to 4 sine theta, just like we had initially. So even though the initial attempt of substituting r negative theta, even though the initial attempt of substituting r negative theta did not work, I'm asking my students to try the other approach of checking for symmetry across the polar axis, which sometimes does work. So though this initially did not work, we would say that this equation that we are about to graph is indeed symmetric about the polar axis. All right, so now I'm not even going to attempt to try to check for symmetry across theta is equal to pi over 2 by using negative r negative theta. I'm going to use r pi minus theta to check for symmetry across theta is equal to pi over 2. So let's begin that process. R squared is equal to 4 sine theta. We substitute in r and pi minus theta. We get r squared is 4 times the sine of pi minus theta. You get r squared is equal to 4. Let's expand the sine of pi minus theta again. We did that already. We got the sine of pi cosine of theta minus cosine of pi sine of theta. We did this already. So we get r squared is equal to 4 sine of pi again. That's 0. All that becomes 0. The cosine of pi, that's negative 1 times that negative. Bring down the sine theta as we did the previous approach, and you end up with the same thing. So this, just like the last problem, is symmetric about every type of symmetry that we're working with these kind of problems. So you can begin the sketching process here. You can begin the sketching process by plotting a series of points. Let's substitute in 0 into r squared is equal to 4 sine theta. We get r squared is equal to 4 sine of 0. Sorry about that. 0. Sine of 0 is 0, and you get 0. The square root of 0 is 0. So you're going to plot the point 0, and the radius is 0. So you're just really plotting a point at the origin. Let's plot another point. Let's substitute in pi over 6. R squared is equal to 4 sine pi over 6. The sine of pi over 6, the sine of 30, that's half. So you get r squared is equal to 4 times half. 4 times half is 2, and the square root of 2 is 1.4. So r is 1.4. So you're going to plot the point at an angle, pi over 6, and you're going to go out a radius of about 1.4. Don't forget, we checked for symmetry. This is symmetric about the polar axis. So you can put a point right here. It's also symmetric about theta is equal to pi over 2. So you can put a point, about right here or so, about radius of 1.4. And this is also symmetric about the pole. So you can extend this out about a radius of 1.4 right there. So again, you solving for 1 point, 1 coordinate, it sort of helps us out because the result is 3 additional points. So it's sort of a good deal. One of the advantages of checking for symmetry prior to doing this problem. Let's substitute in another value for theta. In this case, let's try pi over 4. Let's substitute that into r squared is equal to 4 sine pi over 4. We get r squared is 4 sine of pi over 4. That's, sorry about that. That's 1 over radical 2. Let's put this in a calculator. We end up with 4 divided by the square root of 2, which is 2.8. You take the square root of that, and we get 1.7. So r is equal to 1.7. So you extend up an angle of pi over 4, and 1.7. All right. You get 1.7. Let's see here. It's about right here or so. About right there or so. All right. So now what you, let's see here. Let's check this one more time. We substitute in pi over 4. We got 1 over radical 2. Let me check my math again here. 4 divided by radical 2. You took the square root of that, and you get 1.7. That's right. Let's check this also one more time. Sine of pi over 6 is half. You got 2. The square root of 2, that's about right, 1.4. All right, so everything looks okay. So this is symmetric about the pole. This is symmetric about theta is equal to pi over 2. It's about 1.7, about right there. Something's not looking quite right. I'm a little bit uncomfortable. Let's see here. Well, let's just keep going. 1.4 is about right there. Yeah, 1.4 is about right there. This is also symmetric about theta is equal to pi over 2, or the pole, excuse me. So this would extend out about 1.7, about right there. Okay, about right there. And this would extend about 1.7 across the polar axis. That's about 1.7, about right there. All right. Okay, so again, we plotted. We got pi over 4. We ended up with 1.7. We extended a radius of 1.7 out this way. It's symmetric about the polar axis. About 1.7. That's about 1.7 here. And it was symmetric also about theta is equal to pi over 2. So that's why I went across theta is equal to pi over 2. And it was also symmetric about the pole. All right, so let's keep going. Not quite sure. I think there's another lemniscate, but even though you're a little bit uncomfortable with it, you got to keep going and be confident with your work. All right, so let's look at theta is equal to pi over 3. Let's substitute r squared is equal to 4 sine pi over 3. Another way to say pi over 3 is 60 degrees. The sine of 60, that's radical 3 over 2. R squared is equal to 4. Sine of pi over 3, sine of 60, is radical 3 over 2. You get r squared is equal to 2 radical 3. Let's put that in the calculator. You end up with 2 times the square root of 3. You get 3.5. You take the square root of that, and you get 1.7. You get r is equal to 1. R is equal to 1.7. So you substitute, you got pi over 3. 1.7 is about right here. 1.7. Not forgetting that this was symmetric about the polar axis. 1.7 about right here. It was also symmetric about theta is equal to pi over 2. 1.7 is about right there. And it was symmetric about the pole. 1.7 would be about right there. All right, so you can see the formation of this point, this graph beginning to take shape. Let's also plot maybe one more point, pi over 2. Pi over 2. You substitute that into r squared is equal to 4 sine pi over 2. You get r squared is 4 sine of pi over 2. That's 1. You know, you'd have to know that. R squared is equal to 4. Square root of 4. Square root of 4 is 2. You get r is 2. R is equal to 2. So you plot the point pi over 2, 2. Pi over 2, 2. This is symmetric about the polar axis, so you can put a point right there. And you begin to see the shape that this would take. Looks something like this. Something like 1.4 might be a little bit lower. It would look something like this. Again, you're looking at this shape that's it's called a lemniscate, sort of a bow tie looking type shape, something like this. Something like this. Like a bow tie looking type shape. It's called a lemniscate. Something like that. A figure eight type shape. All right.